Okay, you got the recorder. Okay, first thing first, because I mistakenly set the year of the due date wrong, like 2 years ago. So, and most of you do not know that when the homework assignment was actually due. So I'm gonna make it Wednesday.
It was due 2 years ago.
It was, yes.
We're all late.
Well, yeah, once it was 2 years ago. So it's going to be Wednesday. Okay, the homework assignment is due on Wednesday. This Wednesday.
2 days.
Yeah.
2 days.
In 2 days, yes.
Do you have office hours after this class?
Yes, I do. Yep, that's why I have office hours right after this class. All right. Are there any questions about the homework assignment? If it is a question that's general and everybody seems to have the same question, we can talk about that right now, so that I don't have to answer the question multiple times, and you guys, get to know how the other, people are solving their problem. Is it still problematic?
It's okay. It's just not.
It's not square.
It's not square.
It's legible. It's just kind of bugging me. But
Is it like this? You want it like this? Or?
Actually, the screen isn't square.
Yeah, because the right side looks good.
The screen is leaning. Just
We can deal.
Is it leaning which? Like this?
It's lower on the door side.
No.
I think.
Don't worry about it.
You probably can't fix it.
Yeah, you won't be able to
fiddle
fix
with that all day.
That's weird.
That's fine. Okay, so getting back to the homework, any particular questions, any particular problems that you have encountered? Nothing in particular. Okay. All right, if there's no problem, we will continue to talk about threads, because that's basically the last topic that I have prepared. Yep.
I do want to just confirm one thing. My understanding is that the only thing we actually need to do for this assignment in terms of signals is ignore the
SIG pipe.
SIG pipe. We
Yep.
don't have to do anything with defining masks or anything like that?
No.
Okay.
Mm-mm.
So the bulk of the assignment really is just that timeout.
Exactly. The timeout is the addition on top of the previous socket assignment. It's just that I want you guys to understand, the select call can also have a timeout feature, so that if you're writing an application where bad things can happen to a connection, which they always do, so you can set up a timeout so that one connection breaking doesn't stop your entire program from working all together. And that's basically the purpose of this program. It's just to introduce that timeout aspect to select. Yep.
And is the next assignment for, and is it ready and posted?
The next assignment, Socket 4, is in fact available here. So I think if you click it, you can actually see it.
Okay.
Yeah.
And that's the actual assignment. It's ready to go.
Yeah.
And it's still due 2 years ago.
And they still do 2 years ago. That's right.
I'll try to make a deadline.
I will change the other one first before I forget. But I think you guys are starting to get the idea of how important files are in terms of a Linux or Unix-like operating system. We are using Linux, which is different from Unix, but as far as what we have talked about so far is concerned, they are very much the same. I mean, Unix share almost all the similarities that we have talked about so
Yeah,
far.
it's a day 2.
Huh?
18.
Otherwise, it'll
Oh.
be due already.
10 minutes ago.
Past you already.
You all failed.
All right. So
I do have a question actually on socket 3 that someone
Yes.
brought up in the lab.
Go ahead.
If
Let me
you call
bring
it
that
up
up
down
here.
at the bottom on the zip instructions.
Just hold on a second. Let me find it first.
There it is.
Right there.
There. Because you said to call this the folder exam 2.
Yeah, just do it. As the instruction says. That's fine.
Well, the instructions weren't clear. Where you say turning in the program, but it says executed in the socket 2 folder. Are we supposed to move it from exam 2 to socket 2, or?
Oh, I see what you mean.
And it says to zip it as socket 3, even though it says the name of exam 2.
I'll change the directory name to exam 2, and then later on, I said, executed, try up using the following command. So this should be exam 2.
Okay.
And you want to name socket 3 for the tar file?
Yes.
Okay, that's fine. I was just confused about the different folder.
It was a leftover from last time I taught this class. It was what you are seeing here as a homework assignment with more than 1 week to complete. Because I changed the due date to Wednesday. It was an exam question last time I taught this class, and it was not very well received. Let's just say.
I can understand.
Yeah.
Dr. Techie, do you care what the source files are called? Do you want them to be called socket 3, like socket3.c and so forth?
I think you wanted to just call it socket 2.
Socket 2,
Just
okay.
keep the name socket
Cool.
2. It's fine.
That's what I got.
Do we have to?
Because I've already named mine exam 2.
Yeah, so,
I split
Oh.
mine up into a lot of
Did I change
Yeah,
it?
let's
Did
do
I
that.
did I change it to exam 2? Create a folder. It's okay. I just have to make sure my script leaves me enough room to change the file name. Which file name is the source.
So what is your preferred? You want it exam 2, and then what do you want the .c file to be? You want it in a directory called exam 2, and what would you prefer? You want it to be socket 2?
We just call it socket 2 because most people would use their own socket 2 program to start on this homework assignment. So you already have socket 2 as the name from that homework assignment. So socket 2 is fine.
Okay,
Yep.
thank you.
What if we just make it to where everyone has a makefile? So all you have to do is run make.
But then I still have to find out which executable I have to run to test the program. It's okay. I will figure it out.
But a makefile is okay? A makefile is okay?
A makefile is okay because your socket 2 has a makefile already.
Right.
So you can keep the makefile, and if you want to do the least amount of work, keeping the file name socket2.c is the best way to do it. Okay, very good. Good questions. Now we are back to talk about threads and processes. So we are done with section 4.1. So we'll go ahead and just kind of revisit that particular portion. A thread has the following state. It has global variables, and these are shared with all the other threads within the process. The heap is also shared, and the stack and the stack pointer. Now these are local to each thread. In other words, each thread has its own stack, and each thread has its own stack pointer. Are we doing okay so far? Yep.
How would it work if they each had their own stack but not their own stack pointer?
That's a good question. I can actually answer that question. Okay, years ago, exactly about 14, 15 years ago, when I had to work in a company in Davis, it's an embedded controller, company. The first implementation of a real-time kernel is kind of interesting because what they do is they don't allocate one stack per thread. In fact, there was no concept of a stack. Instead, the stack is being copied around. So there are stacks, but instead of moving the stack pointer from one stack to the next depending on which thread we are dealing with, we move the entire stack around. Yes, it's a mem copy operation every time there is a switch of a task within that real-time kernel.
That seems inefficient.
So to answer your question, in that particular case, we have one single stack and one single stack pointer. It's just that everything is switched and copied. Every single time there's a context switch. When you go from one thread to the next, everything is just being copied around. And also, I also want to make sure that when we talk about this, each thread has its own stack and its own stack pointer. We are not talking about the register itself. There's only one stack pointer register because that's the only one that the processor supports. So what this really means is the stack point, each thread has its own stack pointer. When it's time for that particular thread to execute, then we change the stack pointer to the stack pointer of that particular thread so that it points to portions of its own stack. That's what it means when I say that each thread has its own stack and its own stack pointer. How many of you can relate this to hyperthreading? the concept of hyperthreading with Intel processors. Now you all know what is a core, right? When you have a single core processor, then you only have one single core, and each core only has one stack pointer. When you have a dual core processor, obviously you have two processors, and now each processor has its own stack pointer, and now you have two threads that can really truly execute at exactly the same time. Because you're not just making copies of the stack pointer or only allocating one thread to the stack pointer. You really have two stack pointers. Your two threads can execute in parallel truly at the same time. Hyperthreading is somewhere in between. Okay, if I remember correctly, hyperthreading means the processor has quote unquote spare registers. So to switch from one thread to the next, it just takes like this much time. Instead of, oh, okay, we have to save all the registers, the stack pointer, EAX, EBX, ECX, and EDX, and so on. It's really just like that. Because the entire context is already there. All you're doing is switching which profile becomes active when you execute a program. So does anyone want to correct me? Because I have not actually done a whole lot of research, but that's from my understanding of hyperthreading, that's basically what it is. And that's why hyperthreading makes your program run faster when you have true parallelism. It makes the program run faster, but it's also at the same time not truly another core. Are there any questions at this point, before we move on from section 4.1? How many people still remember last time, right before we ended the class, I described the situation where things can get really, really bad because of variables getting corrupted? You guys do remember that?
You have a clobbered value.
You have a value that's partially updated. So when you use it for comparison, it's okay if it is completely before the update, or it is completely after the update. But if half of the bytes of your variable comes from before and half of the variable comes from after, then when you look at the variable, like an integer all by itself, its value is nothing. It's not from before, it's not from after. The value cannot be used. The worst problem is not just that your variable is corrupted. If it is always corrupted at exactly the same time, every single time you run the program, you can find the problem pretty easily. The trouble is whether that happens or not, when it happens, and which variable gets corrupted, how it's getting corrupted, all depends on the timing of how these threads execute. Now, can you control the switching between the threads when a thread will switch with another thread? It's for the most part asynchronous, which means the timing is unpredictable. So that means you can have a program, like last time I talked about it, that can operate perfectly, flawlessly for years, and then one day it just starts to fail, and every time it fails, it has a different symptom, because the variable that is getting corrupted can get corrupted in different ways. Okay. So we'll go ahead and go ahead.
That's only valid, or that's only a concern if you're modifying things that will be read by your interrupt handlers, correct?
But each thread is parallel. So we're not talking about signal handling or interrupt handling anymore, because the threads are also, they can interrupt each other. So one thread can be partially done with updating a variable, and then the kernel steps in and say, oh, you got enough time, execution time already, it's time to have somebody else to get the execution time. So you still end up with the interleaving of operations that can lead to exactly the same problem.
Is it possible to I can't remember what we called it, but basically where you tell it not to do anything else during that process?
With threading, I think that may be a little bit harder. It depends on the environment. In a Linux type environment, it's harder, because what you need to do is to tell the kernel and say, I'm in a quote unquote critical section. when you have a sequence of updates that cannot be interrupted by other threads, it's called a critical section. And this is not a class to talk about, theoretical operating system concepts. So critical section is one of those concepts. If you have an environment where you don't have an operating system, it's easy to deal with, because what you do is just disable interrupt during that time, and then when you're done with what has to be atomic, which cannot be interrupted, you re-enable interrupt, if interrupt was enabled before. So that's typically how people handle that kind of situation when you don't have an operating system. On the other hand, when you have an operating system, you don't have access to the disable interrupt instruction anymore. It's called a privileged instruction. Because you can imagine, what kind of bad things can happen if one application or user program decides, I want to disable interrupt, and forget to turn it back on. Because if you don't turn interrupt back on, then all the hardware interrupts, like your mouse, the keyboard, your hard drive controller, your network card, and so on and so forth, they cannot be handled, because they will all be blocked.
Every virus would instantly lock up the system.
Yes. The only thing that you can get is the NMI. NMI stands for non-maskable interrupt. It's kind of like kill-9, it's the non-blockable one. So NMI, when you get an NMI, it's usually a very, very serious condition. And it typically connects to what we call a watchdog timer. So this is all kind of we're digressing further and further away from threads, but I think it is important concepts that you guys can, at least hear about, at least for now. And if it's not applicable to what you're doing, that's fine. You don't have to remember it. But if it is, and occasionally you will even see that type of messages. How many people know what is a watchdog timer? Okay, go ahead.
It's a process, sometimes hardware, sometimes software, that monitors to make sure that your primary process is still running and if it is, restarts.
It's basically a timer. A watchdog timer is, it's a hardware timer. In other words, it doesn't depend on software. The software initially would just set up whether we want to enable the watchdog timer or not. And that's typically in the startup process. It could be in the BIOS, could be the early boot stage of your operating system. Once you enable the watchdog timer, it's a countdown timer. Okay, you can imagine it's counting down from 5 seconds, 2 seconds, 10 seconds, whatever. It doesn't matter. It depends on your operating system, what it's doing. Sometimes 2 seconds is more than enough. Other times you might want 200 milliseconds or even less. But when it times out, when that time runs out, the watchdog timer will generate what we call is an NMI, the non-maskable interrupt. Because when the watchdog timer runs out of time and it triggers the interrupt, it means, hey, nobody is around. And sometimes it triggers a system reset. Other times it lets the kernel decide what to do at that point. So how do you prevent the watchdog timer from timing out? Your kernel has to poke it once in a while. Okay, you have to quote-unquote ping it, poke it, prod it, or whatever you want to call it. Basically, you're resetting the timer. Okay, your kernel will basically set up another timer that is blockable. So for the most part, when your operating system is working correctly, it will just do its own thing, and then every so often, it will come back and reset the timer, and give it another 2 seconds, and it will go about do its own thing, go back and reset the timer. But if your operating system, for any reason, cannot go back to reset the timer goes off. The operating system gets the NMI, and depending on how the hardware is set up, it can reset automatically, or the kernel can reset, or you can have 2 NMIs or 2 timers, one to give software one last chance to do something, and the other one just to start reboot the system automatically. And that's what a watchdog timer is. Most computers actually do have a watchdog timer. It's just that most operating systems do not make use of it. It's a very inexpensive device. I mean, it's just a regular timer. But to use it means the operating system needs to cater for that kind of thing happening. And I think most computers that you buy today have a watchdog timer. It's just that the OS usually do not make use of it. It is particularly important in embedded systems and real-time systems. Because in those particular systems, you cannot afford and say, oh, we'll send someone over to turn off the computer and turn it back on again. In many different senses, because one, the device may be at a very remote location where you cannot have access to it. Two, it is also possible that the application cannot afford to wait a few days before someone gets there to reset the computer. It has to be reset like right away, otherwise bad things will happen. So that's what a watchdog timer is.
On the surgical robots, they all have a loop that basically says, if I don't hear back from the instrumentation every so often, I'm going to basically panic, because you don't want to be in the middle of surgery and have something hang up and not realize it.
And then there's a big question in those particular applications: what is considered a safe state?
Yeah.
Yep. And that part is very important, because to control the device, to get itself back into a quote unquote safe state, sometimes it's really just a matter of pull up resistors and some other really simple stuff that you can do on hardware. Other times you need some kind of software to run, a secondary processor to kick in and go, okay, we have to retract all the knives, all the scalpels, or the laser or whatever, turn everything off, retract everything, and just stay there. And that becomes a lot harder, because now you need
to know the path that you can take to retract that signal too.
You basically need what in that case what you need is two paths of control signals. When one path is dead because of the watchdog timer timing out, it will just automatically turn off that side of control signals coming into the robotic control system, and turn on the other one, which its only job is to make everything safe again. It doesn't do anything else. And that can get a little bit more difficult when it comes to hardware implementation, because you need everything needs two ways now. You need a two-way switch for everything. The normal way, and then when bad things happen, switch over to the emergency side. Interesting things. Now, I think we also covered this slide, when to use processes and when to use threads.
Yeah.
I think we did. Oh, we did. Yeah, it's basically just, it depends on how much communication and what type of communication has to happen between the parallel things, okay? When it comes to processes, they don't really have a whole lot of ways to talk to each other. They can talk to each other through FIFOs, okay? Basically pipes, file operations. They can talk to each other through signals, because you can send signals to different processes. And those are pretty much the only two really, really popular ways for processes to talk to each other. Threads, on the other hand, have a lot more tools to talk to each other, because they share global variables. Okay, so that can be very helpful, but it can also be very messy at the same time, because if you do not manage global variables correctly, then you can lead to the problems that we talked about last time, and then your program becomes really hard to debug, because it depends on when the chances happen. So when you have a problem that cannot be easily reproduced, it also becomes very hard to fix and debug. Now, multiprocessing is also not an option when you don't have enough resources. Multi-threading can be supported by relatively little resources, to the point that even if you only have 4 kilobytes of RAM and you're writing programs in C, not in assembly, you can still practically use multi-threading to handle things that are inherently parallel. So that's a really big difference between multiprocessing, where it takes quite a bit more resources, compared to multi-threading, where you can fit everything within a very small footprint in terms of RAM use. The kernel itself, multi-threading itself, as far as the kernel is concerned, can be as small as, in this particular architecture, it's not Linux, okay? Mind you, it's not Linux, it doesn't have a file system or anything fancy like that, but just for the multi-threading part, it's only 2 kilobytes of code. Not 2,000 lines, it's 2 kilobytes of actual code. And that's why multi-threading a lot of times is more practical when you have smaller devices. But when you have big devices like a desktop computer, mainframes, and so on and so forth, multiprocessing becomes an option too. Any questions up to this point? Questions? Moving right along. Linux uses pthreads, and pthreads, the P stands for postfix. It's an OS-independent specification of thread implementation. All POSIX compliant operating systems conform to the same standard. Now, I really should stop here a little bit just to say that Linux is not entirely POSIX compliant. It is from certain perspectives for certain things, but it's not entirely POSIX compliant, and therefore it is not considered compliant. Okay. Any questions up to this point?
Is it just for Unix, or do any other operating systems apply with that standard or have a standard? Is Windows?
Windows NT, I'm not sure whether Windows NT is POSIX compliant. I do not think so. Quickly find out. NTFS, nope, NT, yeah, just Windows NT POSIX. So I guess they can be compliant. Microsoft POSIX subsystem is one of 3 subsystems of several operating systems from the NT family. I think it can create an environment, like a shell type, environment, where within that environment it is POSIX compliant.
But look at the last sentence on the screen.
Starting with Windows XP, the POSIX subsystem is not included as part of standard Windows distribution and has been replaced by Interx. Is an optional POSIX conformant Unix subsystem for Windows NT. So there you go. So it used to be standard, comes with all versions of Windows, or NT-based Windows operating systems. But since XP, it becomes an optional subsystem. But it can be made POSIX compliant. Now you can also look up Linux versus POSIX. Linux, POSIX. Mostly POSIX compliant. That's what Linux is at right now. But so is FreeBSD. So there are a lot of operating systems that are mostly POSIX compliant, but not entirely POSIX compliant. The ones that are truly compliant are here, fully POSIX compliant. A/UX is, I think, is a HP Unix operating system. AIX comes from IBM. BSD is Berkeley Standard Distribution, has been around for a long, long time. DSP Nano, I do not know. I think DSP is digital signal processing, and Nano means it's a tiny operating system. But they chose to make the operating system POSIX compliant. HP UX is also definitely from HP. So AUX may be from someone else. I cannot remember. IRIX is from Apollo computers. It's an older computer. I cannot remember who makes it. Silicon Graphics Incorporated. Do you guys still remember SGI? Microsoft bought most of their patents. They are really good with graphics and graphics engines. Lynx OS, Mac OS 10. Wow, I didn't know Mac OS 10 is POSIX compliant. Minix, which is what Unix Linux should have been, but because of publisher copyright issues, it was never public, and therefore it did not get the popularity that Linux gets. QNX is an interesting one. QNX is a microkernel, which means the actual kernel part, the core part of the operating system. Last time I checked, it was in the range of 30 kilobytes. So it's a very tiny operating system. Everything else, the file system, the networking system, subsystem, everything else are modules on top of the microkernel. And what that makes it so interesting is you can replace modules without having to shut down the entire computer. And because it is so modular, you can, unless you really have to update the kernel portion, you can keep the rest of the system operating when you're replacing one of the modules. QNX is used in nuclear plants and other really mission critical applications. Last time I checked, BlackBerry bought QNX. So I think they had the plans to make their own operating system, for mobile or tablet applications. But I think BlackBerry is in big trouble right now, and that's not panning out anymore.
I get a lot of QNX questions from mechanical engineering departments too, so they're doing something with it.
It's a very suitable operating system for real-time stuff, and that's why it's used in mechanical stuff, because with mechanical stuff, you have real hard deadlines. Okay, the mechanical arm is supposed to grab something, and if you have too much delay, too much lag time, then it fails.
So as far as it being modular, then you can pretty easily bare bone it down to whatever you need exactly.
Yep. So that it means several things. One is also reliability, because if the microkernel is only down to 30, 40 kilobytes, the chances of any remaining bugs in that portion is pretty slim. I mean, there may still be something there, but it's really hard to have any more bugs. And for any other bugs in the file subsystem, you can just replace that module as you find the problems and fix them. But you don't have to bring the entire system down just to fix one particular module. It's a very good operating system. QNX is a very good operating system. There's Solaris, True64 I'm not familiar with. VxWorks is also a real-time operating system. It's very, very expensive. You have to buy the license to use it. But from what I have heard, it's also a very good one.
So is QNX is proprietary as well?
It's proprietary. It's considered a real-time operating system, which means when we say an operating system is real-time, it means the operating system offers you tools so that you, as a software person, can utilize the tools to try to enforce real-time deadlines. With Linux, okay, let's just take our example here. We can set up a timeout for select, right? But how accurate is that timeout? Well, it can be in seconds, can be in microseconds, but it never really gives you a guarantee. Okay, when do your process get time to finish what it's doing? We can set the priority. Okay, with Linux you can set the priority using nice and renice. Those are the two commands where you can set the priority. But nonetheless, there's no guarantee whatsoever. With a real-time operating system, they have ways to truly prioritize threads and processes, where the critical ones will always get more resources, and until they're done, the lower level, the low priority threads and processes do not get any processing time. But we're digressing more and more
That
from our
actually
main
helps me with the
discussion.
problem at work though.
Huh? Sorry?
That actually helps me with the problem at work though.
Oh, well, I'm glad. At least you're getting something out of the digression.
Yeah.
All right, so down to pthreads. Pthread is well documented in the man page, so what you want to do is to do a man 7 pthreads for an overview of pthreads. The first thread and the manager thread. The first thread of a process is started when the process starts. Now this part kind of makes sense. I mean, it makes so much sense that sometimes when we look at it, it doesn't seem to make sense anymore, because we never look at a process and a thread separately. We always look at those things as if they're the same thing, but now we are starting to see, well, maybe we shouldn't be looking at these things as the same thing. So every single time, okay, let me just show you a program. Okay, it's better to illustrate using an example. Today is the 16th. And I'll just call this simple. Here's my program. And it does this. Okay. Where's my pthread call to create a thread? Where's my pthread call to do all kinds of thread-specific operations? There's none, because this particular thread, when you get into a program, it starts with main, and then it executes whatever it does, whatever your program specifies. That's your default thread of that process. You do not need to create it. It comes pre-created and is attached to the process already. Are we doing okay so far? What about the stack? I don't see any calls here or any system call to allocate the stack and tell the operating system, hey, use this part of memory as your stack. It's done by the operating system already. Everything is already done. This is your first thread. Everything is done already. So unless you need additional threads, this one is already done. You don't have to do anything to use the first thread, the default, the manager thread of your entire process. A manager thread is also created when pthreads are used in Linux. This manager thread exists only to create and terminate other threads. It is not the first thread. But that's only created if we're using pthreads. In this case, in this particular simple program, we are not using pthreads, and as a result, the manager thread is not there. The initialization of the first thread and the manager thread is handled in the initialization code that is invoked before main is called. In other words, the allocation of the stack, the initialization of the stack pointer, the initialization of your global variables, and so on and so forth, those all happen before your main subroutine gets control. Okay? How many people have taken assembly language programming where you have to specify the entry point of the entire program? If you take assembly from me, you're raising your hand. Okay? Because in those cases, we have the underscore start symbol, if you still remember. That's the entry point of your assembly language program. And that's the absolute entry point. When your operating system creates the process, loads your program into memory space, fix up all the symbols and whatnot, it starts execution at underscore start. When you have a C program has to link with libc, basically C library subroutines, and inside there, it has its own underscore start entry point. So that's why when you write a C program and you use underscore start as a function name or as some other name that is exported, the linker will complain and say, hey, that's wrong because now we have two underscore starts because one is implied by the C libc library. And then if you give it the second one, the linker doesn't know which one to use. Now you have a duplicate symbol issue. And that's why when you want to utilize pthread, you have to link and compile the program using the -pthread option. Because what it does is it knows now that you have a program that is potentially using pthreads, and the linker will automatically link with the proper initialization part, so that before main gets control, it already starts up a manager thread to support further pthread operations. Yep.
So, does that mean anytime you want to use fork, then you have to compile with the -pthread?
No, fork is process. When you use fork, you're creating a new process.
Oh,
Thread is not a process, so that's why you only do this when you're using pthread, but not when you use fork. The fork is really easy. It's a system surface number. I cannot remember which one, but it's a very simple concept. You can do it easily in assembly code. 5 lines of assembly code, can create a new process. Pthread, on the other hand, is a whole lot more difficult because it's really not just supported by the operating system. It also needs a lot of library subroutines to support it. And here's a very simple program to create a new thread or to utilize the pthreads. And here's the main program. So we start the entry point right here. It doesn't take any parameters. The first part is pthread underscore create. And I think it would be helpful if we bring up the man pages at the same time. So go ahead and bring up man. Pthread underscore create. All right. So if you look at all the parameters, it can take a lot of parameters. The first one is a pointer to a pthread type. In other words, when you have a thread, it has a data structure to represent it. There are certain things in the data structure for sure. The stack pointer for sure is in that data structure. What is the stack pointer for that particular thread? In other words, when a thread is not active, you need a place to remember, oh, this thread is sleeping right now. It doesn't need the hardware stack pointer. But when we want the thread to wake up and do its own thing, where do we want the stack pointer of this thread to point to? So you need that to be stored in the data structure, and that's a part of the pthread_t data structure. So we'll go ahead and kind of go through the parameters, the description. The other part that is also important that has to be mandatory is this part here. How many people can read this and tell me what it is? What is the type of this parameter?
Function, right?
It's a pointer to a function. Okay, I can read this to you. Because we have a parentheses surrounding this part, that means this is a pointer to a function. The function returns a void pointer. It also takes a parameter that is a void pointer. So that's basically what it is. That's the type. But what purpose does it serve in pthread_create? It defines the entry point of that particular thread. Now that's a big difference between a process and a thread. How do we start a new process using fork? What is the quote-unquote entry point of the new process?
The current line of execution.
Sorry?
The current line of execution.
Exactly, after the fork returns. Okay, that's the quote-unquote entry point of the new process. In other words, a process wakes up halfway through the execution of a program. But a thread does not. The entry point of a thread, in other words, how you start a particular thread, is a function. And you have to tell pthread_create what is the entry point of this particular thread. And from your perspective, it is really just an address or a pointer to a function. So you write a function in a specific way so that it is suitable as a thread, the entry point of a thread. This void pointer arg is passed to this subroutine. In other words, when you start up a new thread, you can actually give it something already. The main thread or whatever thread that is starting a new thread can pass quote-unquote parameters, because it takes one void pointer as an argument, and in pthread_create you can also specify what to pass to it. So that means that pointer can be null when you don't have anything to say to the new thread and say, okay, there's nothing to tell you. The new thread is not expecting anything from the thread that is creating it. That's fine. Okay, that's for the most part that's probably what's going to happen. On the other hand, you can have one single entry point where it can have multiple instances. Okay, I can give you one example: motion control. Okay, let's think about motion control. You have one particular thread or one particular function that serves a purpose to move, a motor or an armature or something in a circular fashion, in a certain way. So you now have one single function that contains the logic to control stepper motors, three-phase motors, whatever. It doesn't matter what kind of motor you're controlling, but it has the logic to control it. What if you have 20 motors to control? You find the first line of the subroutine, you find the last line, and you copy it 19 times. Copy and paste, bad. Okay, let's not do it. Then what are we going to do? You create 20 instances, right? You create 20 threads. Each thread will start from the same entry point. Then how can each thread say, oh, I know I'm responsible for motor 19, I'm responsible for motor 3, I'm responsible for motor 2, and this motor is supposed to do this circular motion this way, that one is supposed to turn really fast, and that one is supposed to turn a little bit, stop, turn a little bit, stop, turn a little bit, stop. Where do we store all those things that are motor specific? and let each thread know that you are responsible for that particular motor. What I have just highlighted here. That's what it's for. Okay, this is for creating multiple instances of the same thread, of the same function, so that each thread can have its own quote-unquote parameters. Now, because you're passing a pointer to just about anything, you can make this as simple as a pointer to an integer if that is all you need to communicate with the thread that you're creating. But you can also make this a structure this big if you have that much to say, okay, you thread number blah 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 have to do this, and these are your parameters. So it's a very, very flexible way to control, to pass information to the thread that you're creating, so that it has its own quote-unquote localized parameters, data space, and so on and so forth. Any questions? Yeah.
Are threads scheduled just like processes in terms of when they get CPU time?
That's a good question. I do not know the answer to that. I know that you cannot, with PS cannot show threads. It can only show processes. So when you have multiple threads within a process, I don't know how that is controlled, how the scheduling is done within that context. And then the attribute points to the attribute structure, and the content will be used at the creation. So we have to look at the other one. If you pass a null to attribute, then it will use the default values or default attributes to create the new thread.
As attribute in the thread create,
The attribute is passed by this particular parameter.
Alright, so it's
I think part of that is the initial stack size. How much stack should we allocate for this new thread? The default is probably a certain amount, but if you want to make the stack size a particular amount, you can probably use this feature to control it. So now we can go back to our sample program and take a look at this one. So with this one, this is my entry point. Oh, this is the data structure field associated with the thread. This means I'm not specifying any particular attribute, just take everything by default, it's fine with me. This is the entry point, which is my own function, task1. And this one means I don't have anything to pass to task1. In other words, I just wanted to start executing, and that's it. Are we doing okay so far with pthread_create? As soon as pthread_create returns with a value of 0 as a return value, that means that thread is active already. It starts executing right away after pthread_create. And now we have two threads going on, and they can be both doing things at exactly the same time. Now at some point, if you want the threads to join back into one single one, you can do that. In other words, you can split your execution path to parallel threads when it is appropriate. But at certain times when you say, oh, what this thread is doing has come to an end, it's time to merge that thread back into this main thread, you can use pthreadjoin so that the other thread, so that this will be a blocking call until the other thread comes to an end and go like, okay, I'm done. Then this call will return in the main thread and then continue its own execution. Yep.
Why wouldn't you just cut off that thread in that other thread? Why do you join them back together, or is that conceptually the same thing?
Because you want to synchronize. Because this is a blocking call, which means it does not return. So let's say the main thread gets to this part first, and the task1, the thread that is using task1 as an entry point, is still doing its own thing. So what that means is the main thread will stop and get blocked at this call until the other thread is saying, okay, I'm done, and then the main thread will continue. But when it does continue and error equals to 0 or the return value equals to 0, then it knows for sure that the other thread has already completed up to this point, and now you only have the main thread left to continue execution. It's really useful for synchronization, because sometimes you want to wait until the other one is completely done before you continue with whatever you're doing. And you had a question too.
Complete, it means it just runs the end of its code, or it's just finished executing as far as
I believe so. When
exited the function.
exactly when you return from the function, that's an implicit end of that particular thread. Yep.
The man page we were just looking at actually lists how threads end, and that's one of the conditions, but it discusses them specifically.
A new thread terminates in one of the following ways. Exactly. It calls pthreadexit, so that's an explicit exit. It's just like main or anywhere within your program can say exit 0, so your program just exits at that point. Typically not a very good idea unless you have an error that you cannot recover, so there's no way to continue execution at that point. You can also return from the start subroutine. In other words, whatever subroutine you pass to this one, when it comes to its own natural end at the very end, then it is also considered the end or the exit of the thread. In other words, there's probably an implicit pthreadexit, inside when you use pthreadcreate. It puts it into a shell where when the function returns, there's an implicit pthreadexit at the very end. So it does the same thing anyway. You can cancel a thread. When you cancel a thread, it is canceled from somebody else. In other words, a thread is saying, oh, that thread doesn't need to execute anymore, and you can actively go ahead. It's just like killing a process, except you're terminating not a process, but a thread in this case. If any of the threads in the process calls exit, or the main thread performs a return from main, this causes the termination of all threads in the process. Now, this is kind of interesting. Let's look at, now this part is kind of obvious, okay? When you call exit, you're telling the operating system and say, this process is done, okay? Now the process may have 20 file descriptors still open, 16 threads that are still running, the heap is used up, the stack is used up, whatever. But when exit is called, it's a system service call. Okay? In other words, exit is not return. Exit 0 is different from return 0 because you're not returning to your caller. You are telling the operating system and say, I am done. Okay? Take away all the resources that I have been using, close all my file descriptors, terminate all my threads, and free all the memory that I've been using. So exit 0 is an obvious one because you're terminating the entire process.
So the returns from a start routine, that's what is that exactly? Where
that means in this particular case, when a thread uses task 1 as the entry point, like the one that we are creating here, when task 1 gets to its own end, then
that's the start routine is task 1.
Exactly, for that particular thread. I did make one mistake here. This should be a pointer. Task 1 should return a pointer to void and not just returning void. Because when you read the man page, there's a pointer here. In other words, start subroutine, start routine is a pointer to a function. The function should also return a pointer to a void. And this part explains the attribute, which means if you do not want to use it, you can just leave it as null, then it will just use all the default settings. And this is what we need to look up if we want to find out what it has. Pthread attribute init. Let's go ahead and take a look at that. And pthread attribute. There's a whole family. What this is saying is there's a whole family of calls that start with the prefix of pthread_attr. It never really discloses what the type looks like. It's using, earlier in the description, it describes this type as opaque. How many people know what is an opaque type?
You can't see.
Okay?
It's a type that you don't get to see inside of.
Exactly. When you look up the actual definition of the type, it's probably some really obscure, senseless, structure that has nothing to do with the actual thing. So that means in all these calls, pthread attribute get detached state is casting attr back to the type it should be first before any operation is done. Did you guys take? How many people took P400 from Mr. Fox? I think there was one homework assignment where you have to link with his own object code,
Yes, that sounds
and
right.
he doesn't tell you what the type is. It's only that you have to make calls in order to do something with that particular type. That's an opaque type. It doesn't show you in the header file what it has. What you show you in the header file is just some bogus stuff that has nothing to do with the actual data structure. How many people know or remember what is abstract data type? Okay.
That's just basically you have a setup where you have like it's called like virtual parts. Like it doesn't show you the
It does.
basically has public parts that you have access to, and then you'll be able to, through those public functions or member functions, then you're able to interact with it. But there's a whole.
That's in the context of object-oriented programming, but abstract data type does not need to be object-oriented. Go ahead.
No, I have no idea how to do it in C, but I'm assuming it simply means that certain aspects of it are not specified.
Abstract data type basically means you have a set of subroutines that is associated with a particular type. Structure, class, whatever you want to call it. It doesn't matter. It's a user-defined type. The only way to access or to do anything to an object of that type is through the execution of those functions. Now, in object-oriented programming, it's easy because you can associate member functions with a class. So that makes it really easy. But you can do the same thing with even C or even in assembly, because the key idea is we do not look into the data structure to access each individual member explicitly. We use subroutines to make changes to those member functions and to the data structure. We also use functions to examine those functions. A very good example of abstract data type, some of you took cisp453 from me, and this will be kind of boring, is the remote control. Okay, when you look at this, this is the interface of an abstract data type to the quote-unquote consumers. Okay? In other words, I'm a consumer of a projection system or TV or whatever you want to call it. Do I need to know the inside or the implementation of the projector to use my remote control? Does it matter whether it has little elves inside actually painting the picture, or all I care is I press a certain button, certain things happen, right? Whether it's done by Smurfs or elves or gnomes or other magical creatures, makes no difference to me. Whether it's LCD or not makes no difference to me. Whether it's DLP or not makes no difference to me. That is the concept of abstract data type. This is the abstract data type interface. That's the type associated with the interface. I don't want to know anything that is inside that box. I just want to be able to use it. That's it. Okay, so that concept has nothing, absolutely nothing to do with the language. You can do the same thing in assembly language programming. You can do the same thing in C programming. You can do the same thing in object-oriented programming. But TAC, that's kind of wrong, because in object-oriented programming, we have all these things, called protected stuff, private stuff, so that we can implement our classes so that subclasses cannot modify or access certain things. Well, let me ask you one question. Can the subclasses at least take a look at the header file and know what is being hidden? Yeah, because when you look at the definition of a class, the protect, is it protected or protect?
Protected, I think.
I think it's protected. Protected and the private keywords, they are in the class definition itself. In other words, even though you know as a subclass or a friend class you don't have access to certain things, you know that they're there. Okay? Abstract data type programming means you don't even know what is inside that thing. Okay? And that's basically what we are dealing with here, because when they say ATTR or the attribute of a pthread is an opaque class or opaque type in this case, it means you don't want to find out and you're not supposed to find out and you won't find out.
Yep. What you don't know what a lot of the functions are doing exactly either.
Yeah,
you
but
know the members though, or the
exactly.
variables.
But there's one good reason why you're not supposed to do it, so that you cannot abuse it. They can change the implementation of ATTR, the type, any way they want.
Yeah.
As long as you play by these rules, it would not impact your end of programming whatsoever. Is that making any sense?
And if you don't. And if you don't.
And if you don't and decide and say this is open source and I want to be able to cast my attribute pointer to a certain way so that I can directly manipulate things, then when they change the pthread library to implement things in a different way, your program will start working with no warnings whatsoever. But it's a very powerful concept. It really is a very powerful concept, because in P300, I know I'm kind of digressing again, but this is really important stuff. In P300, we talk about, okay, let's think about a very basic type to represent coordinate, 2D coordinate. Okay, how many different types of coordination system do we have for two-dimensional space? We have the typical x, y, representation. We also have the radius versus angle. Those are the two main types. I'm pretty sure there are additional types too. So if we want to come up with a type definition, struct, class, whatever you want, to represent a point in 2D space, it's easy. Class, open curly brace, int x comma y, close curly brace, we're done. Yes? But if that is what I'm using, then if I want to use a polar coordinate system, well, it's not a big deal. We'll just have to add some member functions, right? So you add a member function, so that r will return the quote-unquote radius, and then theta will return the angle. Because once you have the x and y, you can calculate the other one. Pretty easy. What if I want to change the actual representation from xy to polar coordinate? Well, that gets a little bit harder, because at that point you will have sprinkled code all over the place and say, object1.x equals something, object y.y equals something, and so on. So now you have to change all of that code so that it becomes object1.r equals something, object1.theta equals something, right? But later on, maybe your boss says, oh, guess what? We're going to use this program for something else, and there's another better way to natively represent the coordinate in 2D space. And then you have to change your program all over again. As opposed to what? As opposed to the use of abstract data type, you never start with accessing the definition, the data members of a particular class or type to begin with. Okay? You start off with, oh, we are dealing with xy coordinate, but I do not use something dot x equals something, something dot y equals something. I always say coordinate, set x, and then use the function call to do it. I always use set y to do it, to control the actual coordinate, get x to get the x coordinate, and get y to get the y coordinate. And people look at your program and go like, wow, that's a lot of extra work for nothing. But then when they change the internal representation to radius versus angle, you have to change the implementation of these subroutines. because it's no longer saying, oh, just give me that parameter, I'll store it to the corresponding member function, member field. I have to do some calculation before I can get, before I can change it, before I can store it. But to the rest of the program, there's absolutely no change. You just have to add 2 more functions, because you probably want to add coord set theta, coord set radius, coord get theta, coord get radius. You just have to keep adding more buttons on your remote control. The buttons that you have already still work. Is that making any sense? And that's why, it's not just for programming here, it's also for programming, in general. You do not want to access data members directly. Even though it seems to be a waste of time to define a function just to say, take this function's parameter and copy it to the data member, even if it seems that simple and seems to be a waste of time, do it anyway. Because the compiler can optimize some of this stuff out. You can inline some of this stuff, so that the actual code produced, it is as if you just have an assignment statement. You're not losing any efficiency over that. But later on, if you really need to change the data representation, but want to keep the interface the same way, you don't pay that price later on. So we can see some of this stuff here. Basically, this is the code to display the different attributes, and you can see that you can control how pthread is creating detached or joinable, and so on and so forth. So those are the attributes related to the things that you can associate with a thread. The default values doesn't seem to be shown here. I think each individual call probably has its own. Like this one here, can anyone guess what it does? pthread attribute set stack address. What do you think it does?
Resets the computer.
Does it set the stack pointer?
It let you select where the stack you want. Okay, remember each thread has its own stack. If you say null for attr, it would just use the default method of allocating the stack. This means if you want explicit control of where that stack is, now you can do it instead of using the default. What about the next one? What do you think it does?
Clears the screen.
If the default stack is too big and you don't want to waste resources like that, you can make it smaller. Now the only danger of making the stack size smaller is when you do run out, bad things will happen.
What specifically?
That's a good question. It depends on whether the kernel set it up so that when you try to access out of that memory space, it will give you a segmentation fault or not. If it does not, then it's really, really bad, because basically your stack is growing down, right? So whatever, if you just say, okay, we have a big char array, you define like a 64K, char array, and say that this is my stack. Okay, well, you can do that. When you run out of stack space, in that case, then the stack pointer will keep going lower and lower, which means the global variables that you define before allocating for the stack, those things will get trashed. And I'm pretty sure that's going to happen too, because the stack pointer doesn't have its own space compared to your other variables. So when your stack pointer goes beyond that space that is allocated to it, it would keep going.
So it wouldn't magically get a resized stack.
No, no, I don't think that's the case, and that's always a big problem. Is how do you know how much space you need for the stack? With Linux, it's not too bad because the operating system does offer you some protection. But when you're working with an architecture that only has 4 kilobytes of RAM with no kernel, no protected kernel whatsoever, when you run out of stack space, strange things will happen. Because it would the stack pointer will keep going lower and lower, and it will just trash stuff that is not a part of the stack allocated. And that's a real big issue, and that's why in embedded system programming, we do not use recursion. You can tell Professor Fox recursion is not your friend when you're in embedded system programming. We need everything to be completely predictable. Okay? Now, how would you estimate how much stack space you will need for a particular thread? How would you start with that process if you have to?
Don't dynamically allocate anything. Well, actually.
Dynamically allocating anything is not the issue. You do have to make sure that new, delete, malloc, and free are reentrant. Here's a new reentrant. reentrant, reentrant. That means those calls can be interrupted when you switch from one thread to the other. Okay, let's play out this kind of interesting scenario. Let's say you have two threads, not counting the manager thread because you really don't have control over the manager thread. So you have two threads within the same process. They share a lot of things, global variables. They share the heap as well. So that means both of them can use free and malloc, new or delete, depending on your programming language, to dynamically allocate and deallocate stuff. Okay, that's good. Okay, because now they can communicate very effectively because they can pass messages and say, oh, I'm not going to give you the message by file operations. I'm going to initialize this data structure, pass a pointer to you, and you only have to use this pointer to take a look at data structure, and that's how we communicate. The question is, what if one thread calls new, or malloc to allocate space? Halfway through new, halfway through malloc, the kernel said, hey, thread number 1, your time is up. Okay, all right, we take the control out of thread 1, save its state, make sure that we can come back and continue execution with thread 1 later. And now we move on to thread 2 of the same process. And guess what? Thread 2 is also about to execute new or malloc. So now you have a partially done operation with new and malloc because halfway through that operation, kernel says, oh, thread 1, you're running out of time. And now you have the second thread going into the same subroutine using the same data structures to allocate from the same heap. The question is that safe? Yep.
Am I remembering correctly that there's something to the effect of a heap pointer to indicate?
Yep.
So
a heap has certain bookkeeping data structures to make sure that you can keep track of stuff.
So as long as you update those first.
So the question we're asking,
wow,
look at that. I just have to type is malloc, and then it auto completes thread save. That is what you're looking for. Now I don't have the answer of which call is thread safe and which one is not, but when you use multi-threading in your program, you need to check everything. Do not take anything for granted. Things as simple as printf may not work with multi-threading. Malloc may not work with, is non-reentrant but thread safe. So apparently people do not know. Closed as exact duplicate by cisp453. Reentrant means you can interrupt and call again before the previous reincarnation ended. So that means, okay, mutex. Can anyone kind of guess what mutex is?
Multiple execution?
Nope. It is a locking mechanism that is related to what we just talked about a little bit earlier and also presently what we're talking about. It stands for mutual exclusion. Okay, it is one of the most primitive way where threads can actually lock out each other. Okay, so look at it this way. You have a box. Okay, let's say this box contains everything that you need for new, delete, malloc, and free. Okay. All right. So what mutex is saying that you can only open this box when you have a particular token. Okay. So when I open this box, I'm going to take it away. Not literally, but logically, it's like taking it away. So I'm thread 1. My subroutine called new or delete or malloc or free. So I took that box away. and I'm fidgeting, messing around with this content because I have to allocate space from the heap. The box is no longer available. Okay, it's time for me to give up control. The kernel says I have used up enough time. All right, guess what? I still have the box. I have not released the multics related to the box. And here comes thread number 2 coming in and say, I want to do a new operation too. I need to allocate something from the heap. Comes to here and go like, where's the box? Because everybody who wants to use that box has to call a multics related call first to acquire the mutual exclusion lock. When I have the lock already set and say that I own the box, the next person goes like, oh, there's no box here. Or the box is here, but I cannot access it. So at that point, what happens is the second thread, its call to free or malloc is going to be blocked. In other words, I want to use it, but it's not here. There's nothing else I can do. I'm going to sleep. Now, at that point, the operating system comes in and goes like, oh, good. Since you have nothing to do, I'm going to give thread 1 some additional time. So as thread 1, I come back here. I finish all the things that I need to do. And then when I'm all done, I put the box back here, and I release the multics. I release the lock. Okay. Now the operating system is very smart. Okay. It understands that when I release the lock, when I release the mutual exclusion lock, I can immediately wake up thread 2 because thread 2 is waiting to use this box. And the kernel knows well enough to wake up thread 2 either instantaneously, depending on how the timing and the real-time aspect is done, but it can wake up the other one and come back and say, hey, guess what, thread 2, wake up, the box is available now. Go ahead and use it. So the multics is basically the only mechanism you can use in multi-threading to make sure that the threads do not step on each other when they try to access data structures or anything that requires atomic operation. Okay, so we'll continue this discussion later on. We are running over time a little bit. People are anxious to get into the room. This is also good timing so that we can have new homework assignments on Wednesday.